We begin by introducing the following terminology. If a domain of a linear transformation is equal to its codomain or the target space. So we have a linear transformation T from some vector space V to itself. Such a linear transformation is called a linear operator. So that is linear operators are linear transformations that act from some vector space to itself. The remaining part of this course will be devoted to the study of the structure of linear operators. And eigenvalues and eigenvectors are the main tools to understand this structure. Definition. A non-zero vector V in vector space V is called an eigenvector of a linear operator T from V to V with eigenvalue lambda in F if the following relation holds. So T applied to V is equal to lambda times V. So this means that when we apply this linear operator to the given non-zero vector, the result is the same vector multiplied by scalar lambda. In this case, V is called an eigenvector and lambda is the corresponding eigenvalue. The word eigen is of German origin and it means proper. So here we're talking about proper vectors and proper values of a linear operator. Let's consider an example. Consider a linear operator from R2 to R2 with matrix A, which is 1, 1, minus 4, 5. So let us consider the following multiplication. So 1, 1, minus 4, 5. So let's multiply this matrix by a vector 1, 2. So let's compute the result of this multiplication. So here we take the dot product of 1, 1 with 1, 2. So this is 1 plus 2, this is 3. And the dot product of minus 4, 5 with 1, 2, this is going to be 10 minus 4, this is 6. And what we see is that the image of 1, 2 is actually a multiple of 1, 2. So this vector is proportional to the input vector. So this is 3 times the vector 1, 2. So the conclusion here is that V vector 1, 2 is an eigenvector for operator T or for the matrix A with eigenvalue lambda equals 3. So we point out that in this definition we have a requirement that this vector must be non-zero. So zero vector is not considered to be an eigenvector. Eigenvectors and eigenvalues help us understand the geometry of linear operators. So consider the following operator. Let T be a reflection of R2 with respect to a line passing through the origin. So if we have a vector v, then to compute its image under this linear operator, we consider a reflection. So this will be T of v. Now let us try to understand what are the eigenvalues and what are the eigenvectors in this context. Here, if we take a vector u, which is perpendicular to the line of reflection, so that is a vector that goes like this, which is perpendicular to this line, then t of this vector u will be pointing in the opposite direction. So this will be t of u. And so what we see, we have that t of u in this case is minus u. So this tells us that u is an eigenvector with eigenvalue which is equal to -1. And if we take a vector w, which is a non-zero vector which belongs to the line of reflection, so here we have a vector w which is on the line of reflection, then its mirror image is going to be the same vector w. So what we have is that t of w in this case will be equal to w, right? So if w is on the line of the mirror, then its mirror image is itself. And so the conclusion is that w is an eigenvector with eigenvalue lambda equals 1. So what we see is that for this linear operator, we have two eigenvalues, lambda equals +1 and lambda equals -1. And eigenvectors that correspond to lambda equals 1 eigenvalue, these are non-zero vectors on the line of reflection. And eigenvectors that correspond to -1 eigenvalue, so these are non-zero vectors on the line perpendicular to the line of reflection. We can generalize this picture to the three-dimensional space as well. So let T be a reflection of a three-dimensional space with respect to a plane passing through the origin. If we take a non-zero vector u, which is perpendicular to the plane of reflection, so here we have a vector that looks like this. Then when we take its mirror image, so its mirror image will be on the opposite side. So this will be T of u. And so what we have is that T of u in this case is equal to -u. And so this tells us that u is an eigenvector with eigenvalue lambda equals -1. If, on the other hand, we take some vector W which is in the plane of reflection. So if W belongs to the plane of reflection, so then we have that T of W is equal to W. And then we conclude that every non-zero vector in the plane of reflection is an eigenvector and the eigenvalue is equal to +1. So because so T of W is equal to 1 times W. Again, in this situation, we have two eigenvalues, +1 and -1. And -1 eigenvectors lie on the line perpendicular to the plane of reflection. And +1 eigenvectors are non-zero vectors that lie in the plane of reflection. And it's fairly easy to see that all other vectors that are not on the line perpendicular to the plane of reflection and not in the plane of reflections, all other vectors are not eigenvectors for these linear transformations, because we're not going to get the multiple of the same vector when we take its mirror image. For our next example, let us consider a projection operator. Let P be an operator from R2 to R2 of orthogonal projection to a line. To a line passing through the origin. The picture is like this. So if we have some vector v, then we drop a perpendicular to the given line from v. And so this vector on the line will be P of v. Let's try to understand the eigenvectors and eigenvalues for this operator. If vector u is on the line to which we project, so if u is a vector here, then the projection of this vector will be itself. So the projection will be again the same vector on the same line. So we have P of u will be equal to u. And so this tells us that u is an eigenvector for this operator P, for the projection operator, with eigenvalue lambda is equal to 1. And if W is perpendicular to the line to which we project, so W is a vector that looks like this, then so when we project this vector to the given line, then the projection will be 0. So we see that P of W is going to be the 0 vector. And so this tells us that, again, W is an eigenvector with eigenvalue lambda equals 0. These examples demonstrate that there is a close connection between eigenvectors, eigenvalues, and the geometry of linear operators. Now let I be the identity operator. So I acts from some vector space V to itself. Then every non-zero vector V is an eigenvector for I with eigenvalue lambda equals 1. So this is because I applied to V. So the identity operator does not change the vector. So this is equal to V, which is 1 times V. And if we take a zero operator, so let Z from V to V be the zero operator. So meaning that Z of V is equal to a zero vector for all vectors V in our vector space. Then any non-zero vector is an eigenvector for Z with eigenvalue lambda equals 0, because here we have Z applied to V is equal to 0 scalar times V. Now let us look at a special case. When we take eigenvalue lambda is equal to 0. So what does it mean? So this means that a vector V is an eigenvector with eigenvalue 0. So if t applied to V is equal to 0 times V, which is a 0 vector. And we conclude that V is an eigenvector for operator t with eigenvalue lambda equals 0 if and only if V is a non-zero vector in the kernel of operator t. If a vector space on which a linear operator acts is finite dimensional, we can represent this linear operator with a matrix, and we will be using the notions of eigenvector of a linear operator and eigenvector of a matrix interchangeably. Let us investigate the following question. How can we determine eigenvalues and eigenvectors of a given matrix? Let V be an eigenvector of matrix A with eigenvalue lambda. So this means that A times V is equal to lambda times V. And because we say that V is an eigenvector, so this tells us that V must be non-zero. Let us work with this expression. So let us move all the terms to one side. We will get A times V minus lambda times V is equal to a zero vector. Or this can be written as A minus lambda times identity operator applied to vector V is equal to 0. And this says that the vector V belongs to the kernel of operator A minus lambda I. If we have a non-zero vector in the kernel of a matrix, this implies that the determinant of this matrix is equal to 0. In this equation, we may treat lambda as an unknown, and then we may try to solve this equation in order to find the eigenvalues for which we have non-zero vectors satisfying AV is equal to lambda V. So this equation is called the characteristic equation for matrix A, or for the corresponding operator. Let us consider an example. Let us take a matrix that we already considered before. So we have 1, 1, minus 4, 5. And let us consider the characteristic equation for A. So here we need to take determinant of A minus lambda I. We have a determinant of a difference of two matrices. 1, 1, minus 4, 5. And lambda times I is the matrix lambda 0, 0, lambda. And then we get the following 2 by 2 determinant. We get 1 minus lambda, 1, minus 4, and 5 minus lambda. Let us use the formula AD minus BC to compute this determinant. So here we'll get 1 minus lambda times 5 minus lambda minus the product of off-diagonal elements. So we have minus 4 times 1. So this can be written as 5 minus lambda minus 5 lambda plus lambda squared. And here we have plus 4. And so this simplifies to lambda squared minus 6 lambda plus 9. So we see that this expression, determinant of A minus lambda I for a 2 by 2 matrix, is a quadratic polynomial in lambda. And then the characteristic equation for this matrix is the quadratic equation. Lambda squared minus 6 lambda plus 9 is equal to 0. And this is the same as lambda minus 3 squared is equal to 0. And so we can see how this solves. So we see that lambda must be equal to 3. This tells us that matrix A has a unique eigenvalue lambda equals 3, because 3 is the only root of the characteristic equation. Let us find the eigenvectors corresponding to this eigenvalue. So let V be an eigenvector for A with eigenvalue lambda equals 3. So what does it mean? So this tells us that A times V is equal to 3 times V, or equivalently, this says that V belongs to the kernel of the matrix A minus 3i. So the matrix A minus 3i is the following. So we subtract 3 from the diagonal entries of matrix A. And so this gives us minus 2, 1, and minus 4, and 5 minus 3 is 2. So we see that here we have two proportional rows. So if we apply an elementary row operation, new row 2 is row 2 minus 2 times row 1, then the matrix that we obtain will be -2, 1, 0, 0. And so then if we divide the first row by -2, we'll get the matrix 1, -1/2, 0, 0. So here we need to describe the null space of this matrix. So we see that x2 is a free variable. So we say that x2 is equal to t, and x1 is then equal to 1/2 t. And so then we get the null space of a minus 3I is the following. So we'll have x1, x2 is equal to t times 1/2 1, or we can also write this as t over 2 times 1, 2 to avoid fractions in the vector. And our conclusion is that lambda equals 3 eigenvectors are non-zero multiples of the vector 1, 2. And this agrees with what we saw earlier. We saw that if we take this vector as v, then earlier we saw that a times v is equal to 3 times v. And so we saw that this vector was indeed a lambda equals 3 eigenvector for this matrix. And here we saw that we can use a characteristic equation in order to find the eigenvalues and find the eigenvectors. Let us present a summary. How to find eigenvalues and eigenvectors. First, compute the characteristic polynomial. Which is determinant of a minus lambda I. And here we treat lambda as a variable. Then solve the characteristic equation. Determinant a minus lambda I is equal to 0. So we compute the characteristic polynomial, and then we equate this characteristic polynomial to 0. Then eigenvalues are precisely roots of the characteristic polynomial. A characteristic polynomial may have several roots. Let's call them lambda 1, lambda 2, lambda k. So then, for each eigenvalue lambda j, compute the null space of the matrix A minus lambda j times identity. And eigenvectors corresponding to eigenvalue lambda j are non-zero vectors in this null space. We know that the null space of a matrix is a subspace. So if we take null space of A minus lambda I is a subspace in V. And non-zero vectors in the subspace are eigenvectors corresponding to eigenvalue lambda. So this subspace is also called eigenspace of A corresponding to lambda. The only delicate point here is that 0 vector belongs to the eigenspace, but it's not considered to be an eigenvector, because by our definition, eigenvectors are non-zero vectors. So, however, usually when we want to describe a null space, we are going to find a basis in the null space. And basis in a subspace consists of non-zero vectors. So all vectors in the basis will be eigenvectors. And so this minor distinction between eigenvectors and vectors in the eigenspace will not pose any difficulties for us. So we call lambda in F an eigenvalue of matrix A if the eigenspace corresponding to lambda so this is kernel of A minus lambda I, and we will use the null space and the kernel interchangeably. So if this kernel is different from just the zero vector. And as we saw, this is equivalent to saying that lambda is a root of characteristic polynomial. Determinant of A minus lambda I is equal to 0. Let us consider one more example. Consider the following matrix: 4/5, negative 3/5, negative 3/5, negative 4/5. So we want to find eigenvectors and the eigenvalues for this matrix. So we begin with characteristic polynomial. Determinant of A minus lambda I. So if we subtract lambda from the diagonal entries, then we get the following 2x2 determinant: 4/5 minus lambda, negative 3/5, negative 3/5, and negative 4/5 minus lambda. Now, let us pull out the factor of 1/5 from the first row and from the second row. So then we get 1/5 squared times the following determinant: 4 minus 5 lambda, negative 3, negative 3, and negative 4 minus 5 lambda. Now, this becomes 1/25 times, so here we get 4 minus 5 lambda times negative 4 minus 5 lambda minus negative 3 squared. So this becomes 1/25 times, so if we switch signs in both of these factors, then this will be 5 lambda minus 4 times 5 lambda plus 4, and all of that minus 9. And using the formula A minus B times A plus B is equal to A squared minus B squared, we get 1/25 times 5 lambda squared minus 4 squared and minus 9. So this becomes 1/25 times 25 lambda squared, and 16 plus 9 is 25, so we get minus 25. So this is lambda squared minus 1, And this is our characteristic polynomial. So next, eigenvalues are roots of the characteristic polynomial. So we are solving the equation lambda squared minus 1 is equal to 0. But here this easily can be factored. So this is lambda minus 1 times lambda plus 1 is equal to 0. And what we see is that the eigenvalues are lambda 1 is equal to 1 and lambda 2 is equal to minus 1. So this tells us that this matrix has two eigenvalues, plus 1 and minus 1. In order to find eigenvectors, we're going to treat each eigenvalue separately. So first we consider eigenvectors for eigenvalue lambda 1 is equal to 1. So here the matrix that we take is A minus identity. So this matrix becomes, so we take lambda equals 1 here, so we get negative 1/5 and negative 3/5 and negative 3/5, and here we get negative 9/5. And what we need to do is we need to find the null space. In order to find the null space, we need to do row reduction. So first we say new row 1 is equal to negative 5 times row 1. So this will create a pivot for us. And then the matrix that we get will be 1, 3, negative 3/5 and negative 9/5. And then we eliminate this entry by saying that new row 2 is equal to row 2 plus 3/5 of row 1. And this gives us the matrix 1, 3, 0, 0. We want to point out is that when we have an eigenvalue, then this null space is going to be non-trivial. So this means that in this reduction, we are guaranteed to have a row of zeros. So if you find an eigenvalue and the null space for this A minus lambda I does not lead to a row of zeros, so this means that there is an error in arithmetic. So either the roots of the characteristic polynomial were found incorrectly, or there is an error in row reduction. So if things go right, then we are guaranteed a row of zeros in the row echelon form of the matrix A minus lambda I. So here we assign the parameter t to a free variable x2, and then x1 is equal to negative 3t. So x1, x2 is a t multiple of a vector negative 3, 1. And our conclusion that basis of lambda equals 1 eigenspace is a single vector negative 3, 1. So this eigenspace is one-dimensional. And this vector minus 3, 1 is an eigenvector of this matrix corresponding to eigenvalue plus 1. Now let us deal with the second eigenvalue. So let us find eigenvectors for eigenvalue lambda 2 equals negative 1. So here deal with the matrix A plus I. So this is A minus minus 1 times identity. So this matrix will become 9 over 5, negative 3 over 5, negative 3 over 5, and here we'll get 1 over 5. And we need to find the null space of this matrix. So we do row reduction. So our first step is we say row 1 new is 5 over 9 times row 1. So to create a pivot, so then this will become 1 negative 1/3, negative 3/5, 1/5. And then we say that new row 2 is row 2 plus 3/5 of row 1. And this will eliminate the second row. So the matrix, the reduced row echelon form will be 1 minus 1/3, 0, and 0. To describe the eigenspace, we assign t to the free variable x2, and then x1 is equal to 1/3 t. And so then x1, x2, now to avoid the fractions in the eigenvector, we can pull out t over 3, and then we get 1 and 3. And we conclude that lambda equals -1 eigenspace is also one-dimensional, and basis of lambda equals -1 eigenspace is a single vector 1, 3. Now let us interpret these results. So here we have lambda equals 1 eigenvector -3, 1. So this is a vector that goes like this, right? And so the eigenspace is one-dimensional, so it's a line spanned by this vector. This transformation preserves vectors on this line, because if we have a lambda equals 1 eigenspace, so this means that t of v is equal to v, when v is a lambda equals 1 eigenvector. So vectors on the line spanned by vector -3, 1 do not move under this transformation. The second eigenvector, lambda equals -1 eigenvector, is the vector 1, 3. And so what we see is that actually these two vectors are perpendicular to each other. And for this vector, so let us call it w, we have t of w is equal to -1 times w, or simply minus w. So this means that this transformation flips all vectors that are on the perpendicular line. So t of w is equal to -w. So what we see is that geometrically, this transformation is nothing else but a mirror reflection with respect to this line. And this line has equation x plus 3y is equal to 0. So the machinery of eigenvalues and eigenvectors allowed us to see the geometry behind this matrix. By determining eigenvalues and eigenvectors, we were able to see that this is a matrix of a reflection operator. Thus, a conclusion that eigenvectors and eigenvalues allow us to understand the structure of linear operators. To conclude this lecture, let us discuss the properties of characteristic polynomial. Let A be an n by n matrix. Let us compute the characteristic polynomial. So we have determinant of the following matrix: a11 minus lambda, a12, dot, 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 a1n, a21, a22 minus lambda, a2n, and so on. And the last row will be an1, an2, and the last entry is ann minus lambda. When we compute this determinant, we see that the highest power of lambda will be lambda to the power n, which will come from the product of the diagonal entries. So we can write the characteristic polynomial for an n by n matrix as bn times lambda to the power n plus bn minus 1 lambda to the power n minus 1 plus dot 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 plus b1 lambda plus b0. What can we say about the values of these coefficients? Well, first of all, we can easily determine the leading coefficient. So the leading coefficient will be minus 1 to the power n. And so this means that for when n is even, so this coefficient will be plus 1. And when n is odd, the coefficient will be minus 1. This is because we have n negative signs in front of lambda on the diagonal. Another coefficient that has a special meaning is the coefficient b0. Now, what is the value of b0? So if we denote the characteristic polynomial by p of lambda, then, so this is determinant of a minus lambda I. Then what is p of 0? So this will be determinant of a minus 0 times I, or simply determinant of a. But what's the value of a polynomial at 0? So the value of polynomial at lambda equals 0 is the constant term. So this means that b0 is equal to determinant of the matrix A. One more coefficient that we can easily determine is the coefficient bn minus 1. When we computed bn, we noticed that the coefficient bn comes from the product of the diagonal entries. It turns out that the coefficient bn minus 1 also comes from the product of the diagonal entries. When we compute the term with lambda to the n minus 1, we need to take n minus 1 factors from the diagonal entries. But then it turns out that there is only one way to complete it to a permutation matrix. So if we have chosen n minus 1 entries on the diagonal, then to get a permutation, the last entry also has to be on the diagonal. So this tells us that if we want to understand the coefficient at lambda to the n minus 1, all we have to do is we have to look at the product of diagonal entries. So we have a11 minus lambda times a22 minus lambda times ann minus lambda. So as we saw, that the leading term here is when we take the product of n factors of minus lambda. So we have minus lambda to the power n. Now, what will be the coefficient at lambda to the n minus 1? Well, one possibility is we can take factors lambda or minus lambda from the second, third, and the nth factor. And we take the constant term a11 from the first factor. So this will give us minus 1 to the n minus 1 times a11. Then we can skip the second factor and take minus lambda from the first, third, and up to the last factor, and take a22 from the second factor. So this will give us minus 1 to the n minus 1 plus a22. And so on. So the last term with lambda to the n minus 1 will be when we take minus lambda from the first n minus 1 factors and a and n from the last factor. So what we get is the sum a11 plus a22 and plus a and n. So this brings us to the following definition. The sum of diagonal entries of A is called the trace of A and denoted TR of A. And what we see is that the coefficient bn minus 1 is equal to minus 1 to the n minus 1 times the sum of the diagonal entries of a matrix A. So it's minus 1 to the n minus 1 times the trace of A. These relations make it very easy to compute characteristic polynomials of 2 by 2 matrices. In this case, determinant of A minus lambda I is equal to lambda squared, so because minus 1 squared is plus 1, minus trace of A times lambda and plus determinant of A. So if we consider an example that we already discussed in this class, 1, 1 minus 4, 5, then characteristic polynomial P of lambda is equal to lambda squared minus trace of this matrix is the sum of diagonal entries. 1 plus 5 is equal to 6. So we get 6 lambda. And plus the determinant of this matrix, which is 1 times 5 minus negative 4 times 1. And so what we get is lambda squared minus 6 lambda plus 9.